right, so we've already found the volume of a solid that was revolved around certain horizontal axes, but now we're going to look at what happens when you rotate around something like the y-axis, so a vertical axis. When you take a look at the graph over here, we have the shaded region, and we're going to rotate it around the y-axis, which is the opposite direction from before. So we have these two equations, y equals plus or minus square root of x, and we have y equals x minus 2. So the first difference that you have to consider is that if you're rotating around a vertical line, that you have to make your equations in terms of y instead of in terms of x, which means you have to solve for x. So for example, y equals plus or minus square root of x is going to be x equals y squared. So square both sides. Same idea for y equals x minus 2. Now that's going to be y plus 2 equals x. So thinking back to our general volume formula of pi times our integral from a to b of our outer minus our axis squared minus our inner minus our axis squared dx was our normal formula. It's going to be the same thing except this part right here is going to be a dy. So for our equation we're going to have pi times the integral. We'll come back to the bounds in a second. When we're looking at the y-axis, the graph that's further away is this linear graph. That's going to be our outer graph. So that's y plus 2 equals x. So y plus 2 minus our axis is just 0, minus our inner function is that parabolic shape, that's y squared, minus our axis is 0 squared, and now that's dy. Now, this looks different because we're using y's, but if you're going to type it in your calculator, you'll still use x's. You just have to make sure you have the same variable everywhere. So if you go ahead and type that in your calculator, you should end up with 45.2389. And what you'll notice is this is exactly the same problem that we had before. It's just turned on its side. And then so I actually forgot to go back. Let's talk about the bounds so that you can actually type it in your calculator. So we have these two coordinates here for our bounds. What you have to make sure of is you're going to use the y coordinates instead of the x coordinates. So it's still from -1 to 2. So now you can see that it's exactly the same as the example that we had before. All right, so let's talk about other axes that we could rotate it around. So if we rotate around the line x equals 4, that's our next one. So x equals 4 is this vertical line right here. And now it's going to switch which graph is my outer graph and my inner graph. Now I'm further away from the parabolic graph and closer to the linear graph. So if we want to find that volume, same idea, pi, we're still going to have the integral from -1 to 2. Our outer function is now the y squared minus our axis, which is 4, all squared, minus y plus 2, our closer function, minus 4 quantity squared, dy. Still dy because we're rotating around a vertical axis. And then if you want to simplify that, pi times the integral from -1 to 2, y squared minus 4 squared, minus y minus 2 squared. Just simplify that a little bit. And if you calculate that, again with your calculators, using x's in your calculators, you would get 67.858. All right, the line x equals 7 is going to be just the same because when I look back at my graph for x equals 7, it's still to the right of this graph, so it's going to be just the same as x equals 4. So all I'm going to do is change the axis. So pi times the integral from -1 to 2 of y squared minus 7 squared minus y plus 2 minus 7 squared dy. So pi times the integral from -1 to 2, y squared minus 7 squared minus y minus 5 squared dy. And that will give us 152.681. All right, so let's move on to a different type of solid. So not just solids of revolution. The other type we're going to see on the AP test are solids with known cross sections. So what you have, you can see in this picture here, you have some base shape and then you're building shapes on top of it. So in this picture we have squares. We're adding squares onto the top. Or over here we have triangles. And so just keep in mind that our general formula that we talked about before to find volume is it's the integral of the area of the cross section. So that's the shape, like if I were to slice the graph or the figure, that's the shape I would see. So when we had solids of revolution, that area was a circle. So we had done the integral of pi r squared. And when we had washers or the donuts, we'd do pi big R squared minus pi little r squared. So it's the same idea here, we're just going to have different shapes now. So let's take a look at a square. So think about the area of a square. The area of a square is just side squared. So in this case, we have to figure out what our side is. And so looking back at the graph, the base of the square is going from one graph to the other. So it's kind of hard to see here, but you have an f of x and a g of x at the top. So the base is going to be f of x, the top graph, minus g of x, the bottom graph. And if this is a square, then this side will also be f of x minus g of x. So the area of our cross section, the square, will just be f of x minus g of x quantity squared, just side squared. So to find the volume, we basically add up the squares. And remember that when we say adding up, we're really talking about an integral here. So our formula that we're going to use if we have cross sections that are squares will be the integral from a to b, f of x minus g of x quantity squared. And so notice this looks a little bit different than the equations we were using before. We would have like f of x squared minus g of x squared. This is the whole quantity squared, so the difference squared. All right, we're going to do the same idea with a triangle, except our area formula is 1/2 base times height. So we're assuming that we have a right triangle here, and they're isosceles, so the height and the base are the same. So here our base is f of x minus g of x, and our height is f of x minus g of x. So the area of the triangle will just be 1/2 base times height. So f of x minus g of x times f of x minus g of x, which gives us 1/2 the quantity f of x minus g of x squared. And again, to find our volume then, we're just going to integrate that. I am going to take this constant out in front. So 1/2 the integral a to b of f of x minus g of x squared dx. So notice it looks a lot like the formula that we had for our squares, except this constant out in front has changed. All right, so let's go on to some other shapes. Equilateral triangles. So now we're testing your geometry knowledge and memory. We've talked about this formula before. Area of an equilateral triangle is square root of 3 over 4 sides squared. So notice again the base is going from your top graph to your bottom graph. So f of x minus g of x still. Okay, so if that is our base, that's basically our side for this equilateral triangle. So our area formula will be square root of 3 over 4 times our side, f of x minus g of x, the whole thing squared. And so then our volume, we just integrate that same formula. Square root of 3 over 4, the integral from a to b of f of x minus g of x, quantity squared dx. So you can see a lot of this is based on your memory of your geometric formulas. If you don't remember the square root of 3 over 4, it makes the problem a lot harder. Okay, let's look at semicircles. So notice here semicircle goes again from one edge of the graph to the other. However, that's the diameter, is f of x minus g of x. So if I want to think about the radius, just this part here, which is what we use for a semicircle, that would be 1/2 f of x minus g of x. And so our area of a semicircle is pi r squared over 2, or 1/2 pi r squared. And so our area will be pi, I'll put the 1/2 out in front, it makes it a little easier, times 1/2 f of x minus g of x, and it's that whole piece squared. Which means I have to square the 1/2 and the f of x minus g of x. So I have 1/2 pi times 1/4 times the quantity f of x minus g of x squared, which gives us a total of 1/8 pi times f of x minus g of x squared. And so again, our volume, we're just going to integrate that. So 1/8 times the integral from a to b. Oh, I should have put pi over 8 out in front. Pi over 8 times the integral from a to b of f of x minus g of x squared dx. So hopefully what you notice here is a pattern. Our integrand was always f of x minus g of x quantity squared. And we're assuming here that f of x is bigger than g of x. It shouldn't make a difference if you're squaring it, but usually you want to do top minus bottom. And the only thing that was changing was your constant. So for semicircle, it was pi over 8. For equilateral triangle, it's square root of 3 over 4. So if you can just remember that, it will make these problems a lot more straightforward. If you forget, that's when it's going to get more challenging. So let's try this out. We have our lovely graph here. We've seen this graph before. On top is sine of pi x, and on bottom we have x cubed minus 4x. And so we're going to use those formulas we just had on the other page. So first we have equilateral triangles. So our formula is volume square root of 3 over 4 times the integral from a to b. So in this case it's 0 to 2. So you have to use your intersection points. Our top graph is sine of pi x. Our bottom graph is x cubed minus 4x. So you need to make sure to use parentheses there or distribute and change the signs. And then from there you can just type it right into your calculator, 4.3207. For semicircles, our constant is pi over 8 times the integral from 0 to 2. Our integrand is going to be just the same. I'm going to simplify it this time, minus x cubed plus 4x quantity squared dx. And that will give you 3.918. All right, isosceles right triangles, our coefficient was 1/2 times the integral from 0 to 2 sine of pi x minus x cubed plus 4x quantity squared dx. And that gives us 4.989. And squares, it's just the integral from 0 to 2 sine of pi x minus x cubed plus 4x squared dx. And that will give us 9.978. These last two examples are a little bit different. We have rectangles whose height is twice the length of the base. So our area formula, which is base times height, now becomes base times 2 base, or 2 base squared. That's just telling us our coefficient is going to be 2. So we'll set that up. 2 times the integral from 0 to 2 sine of pi x minus x cubed plus 4x dx. And if our height is 1/3 the length of the base, then our area is base times 1/3 the base. So that will just be 1/3 the integral from 0 to 2 sine of pi x minus x cubed plus 4x dx. And that gives us 3.326.